Okay, hello everyone. In a new video, then we have reached part 4 of chapter 9, which is the chapter of equilibrium of a body in the third unit of mechanics. Then in this one we are going to solve more exercises. Then we have reached exercise 10, section 14. The object of this exercise is to calibrate a spring S by studying the variation of the value T of its tension. Then here, T without a vector represents the magnitude of the tension vector, T vector, as a function of its elongation x. For this, we consider a spring S, a graduated ruler, and some marked masses. Then the graduated ruler is to measure the elongation x, or the final length, for example. We denote by L0 the length of the unloaded spring. Then L0 is the initial length. And by L the length of the spring when a marked mass of mass M is suspended from it. Then L is the final length. Then the moment we specify the initial length and the final length, the elongation can be calculated from x is equal to L minus L0. This marked mass being then in equilibrium, so at any moment in this exercise we can use the condition of equilibrium. Theoretical study, the marked mass is in equilibrium. Take L0 is equal to 10 centimeters and G is equal to 10 newtons per kilogram. So G is equal to 10 newtons per kilogram. It means that each kilogram is being acted by 10 newtons, which reflects the fact that this experiment is being performed on the surface of the Earth. Now we know that the value of L0 is given by 10 centimeters. Knowing that centimeters is not a unit of length, in order to convert from centimeters to meters, we divide by 100. Then 10 divided by 100, this is equal to 0.1 meters. Now, so here we are in 1.1. Knowing that the mass is in equilibrium, write the expression that represents the condition of equilibrium of this marked mass. So always as a title we start by at equilibrium. Then on the left hand side of this equation we write the different forces acting on the mass, and they are given by the weight and the tension. They mention the tension, and because we have a mass it will be subjected to the weight. This is equal to the zero vector. Now dragging T to the right hand side, then W is equal to minus T. So the first equation tells us that both forces have the same line of action the effect of the forces acting on the mass cancel each other, whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Now in 1.2 we need to deduce the expression of T as function of M, and by deduce it means that we need to use the previous part. In the previous part we discussed the condition of equilibrium, which is the relation between W and T. Now here they are telling us T as function of M, so notice that this is a magnitude. In order to extract the magnitude of this equation, we will write it down. And let's say in magnitude, so in this case we drop down the vectors and we remove the minus sign, so weight is equal to the tension. But we know that the weight can be expressed as function of M, and it's given by M multiplied by G. Then in this case the tension is equal to M multiplied by G. So the new additional equation that we have is that the tension is equal to M multiplied by G. Now in number 2 they are telling us a graphical study. The results of the measurements are tabulated in the table below. 2.1 copy the table and fill the empty boxes. The table consists of 4 rows and 5 columns. Let me draw it down. Then the first column consists of the following quantities: so the mass in gram, now the length in centimeters. Let me make it clear that this is centimeters, the tension in newtons, and the elongation x in meters. The given values are given by 50, 100, 150, and 200. As for the second row, 15, 20, 25, and 30. And let's complete the rest. Now, the third row, which is the tension, can be completed because we know that tension can be calculated from M and G. And recall that whenever the exercise consists of two parts, it means that something from the first part must be involved in the second part, which is given by this relation. And we know that the value of G is given by 10 newtons per kilogram. So here, let me convert these masses to the SI, then 50 divided by 1000 in order to convert from grams to kilograms. It will be given by 0.05 kilograms. So this is 0.05 kilograms. Then 100 divided by 1000 is given by 0.1 kilograms. 150 divided by 1000, this is 0.15 kilograms. And 200 divided by 1000, this is 0.2 kilograms. Now let me calculate the corresponding tensions. That are given by, so we have that T is equal to M multiplied by G. We know that the value of M is given by 0.05 and the value of G is given by 10, so this is 0.5. Everything is expressed in the SI, so this is in newtons. Now as for the other tension, so let me say this is T1, so this is 0.5. Here we don't include any unit because the unit is included in the first column. As for the tension T2, which is equal to M multiplied by G, which is equal to 0.1 multiplied by 10, which is equal to 1. Everything is expressed in the SI, so this is 1 in newtons. Now T2 is equal to M multiplied by G, which is equal to 0.15 multiplied by 10, which is equal to 1.5 in newtons. This is T3. And as for the final tension, 0.2, multiplied by 10, this is equal to 2 newtons. So this is 0.5, 1, 1.5, and 2. So this is it for the third column in the third row in the table. Now let's complete the final one, which is x. Recall that x mainly can be calculated using two methods, either from Hooke's law or from the fact that x is equal to the final length minus the initial length. Here we are lucky because we know that the initial length is given by 10 centimeters and we know the final length. So for each column we can calculate what is meant by x, which is the difference between the initial length and the final length. So let me say that x1 here, as a part of the answer, the student must show the calculation. So x1, which is equal final length minus initial length. Now the final length is 15 minus the initial length, which is 10. So this is equal to 5. Since both this and this are expressed in centimeters, then this is in centimeters. In order to convert from centimeters to meters, we divide by 100. Then 5 divided by 100, this is equal to 0.05 meters. So here is 0.05. Now x2, which is the elongation corresponding for this column, the length is 20 minus the initial length, which is 10, so this is equal to 10 centimeters. Then 10 divided by 100, this is equal to 0.1 meters. Now as for x3, which is the final length minus the initial length, which is given by 25 minus 10. So this is equal to 15 centimeters, since both this and this are expressed in centimeters. Then 15 divided by 100, this is equal to 0.15 meters, and with no exception, because we can notice the pattern, then x for the final one, it will be 0.2. But let's complete it, and let's show the calculation, since the calculation is the part of the answer. Then L minus L0, which is equal to, the final length is given by 30, minus 10, which is equal to 20 centimeters, then 20 divided by 100, which is equal to 0.2 meters. So this is it for 2.1. Now in 2.2 they are telling me plot the calibration curve of the spring that represents the variation of t as function of x. Let me make some space. Now because we need to plot a curve, and the curve can only be plotted in an orthonormal system or a system of axes. So it will be given by t as function of x. So it's always convenient to take a look on the values that we have. We need to plot the curve. So okay, on the ordinate axis, which is represents y, now I will give you another method in order to know. So okay, notice that if you follow the title given in the exercise, they are telling us the variation of t as function of x. So the first variable that comes, this means that it must be on the y-axis, and this can be verified by referring to the scale, since they are telling us the axis of ordinate is 1 centimeters. Ignore this and this. So newtons, then indeed on the ordinate, which is y-axis, then we need to place t. And as function of x means that x must be on the x-axis, and indeed when they are telling us abscissa, which means x, we have that it's labeled by the quantity 0.025 meters, so they are in agreement. But before we plot the curve, we need to take a look on the values. They are telling us 0.25 newtons, and the maximum value that we want to plot is 2 newtons. Okay, so we need like 8 divisions along the y-axis in order to reach 2. So starting from 0, 0.25, 0.5, 0.75, 1, 1.25, in order we reach 2. Then almost we need 8 divisions along the y-axis. As for the x-axis, having 0.0025, and we need to reach a maximum value of 0.2. So almost we need to reach, also we need 8 divisions. Now using a pencil and the graph paper, if the number of divisions is not sufficient to label these quantities, you can erase and either increase or decrease the length of the axis itself. So here let me say 1, 2, 3, 4, 5, 6, 7, 8, 9. And along the y-axis, let me say that we have 1, 2, 3, 4, 5, 6, 7, 8, and 9. And let me drag these downward. Okay, so now we have placed these axes. Recall that the length of the axis is not a problem. While we label the points, we will check whether this number of divisions is sufficient to plot the values on the table or not, on the graph or not. Now let's proceed. Now we need to label these axes by the corresponding quantities. So if you recall the title, the first one that comes after the variation, it will be represents the y-axis. So this is the tension T, and its value can be extracted either from the table or from the scale itself. So this is in newtons. As for the x-axis, it's labeled by x. Then this is x, which is in meters. So this is the origin O. Now let's label the points. So what we have here is that, okay, now we need to divide these axes, labels them. So on the x-axis they are telling us each 1 centimeter corresponds to 0.025 meters. Let me make some space. So we are done with these calculations because they are already in the table. Then the scale, let me write it here, and here I'm leaving a space for the title, knowing that along the x-axis, which is the abscissa, each 1 centimeter corresponds to 0.0025 meters. So let me say that this is 0.0025, this is 0.05, this is 0.075, this is 0.1, 0.125, 0.15, 0.175, and this is 0.2. Okay, so upon moving each division I am adding a value of 0.025, and this can be upon moving each division I'm adding 0.0025, and this can be done by referring to this one, each 1 centimeter increased by 0.0025. Now as for the y-axis, upon going each centimeter upward, we need to increase the value by 0.25. So 0.5, 0.75. So this is 1, this is 1.25, this is 1.5, this is 1.75. And this is 2. Now let's plot the points. So the first point is given by this couple, which is 0.05 for 0.5. So this is the first point. Now the second point is for 0.11. This is the second point. The third point is 0.15, 1.5. And the final point, which ends here, corresponding for 0.2 and 2. And now we didn't represent the curve. This is the curve. Now it's left to write the title. The title again can be extracted from the question itself. So this curve, or the calibration curve, represents the variation of t as function of x. Then the calibration curve, or this curve, as function of x. Using the calibration graph, determine the value of the stiffness k of the spring. So we know that always and forever k can be calculated using Hooke's law. Here we are free to use either method. Either we use the slope method, in which we write the definition, we choose 2 points. Then we calculate k, we convert them to the SI, they are already in the SI. Then we say that k is TA minus TB over XA minus XB. The other way around is very simple, it's just apply Hooke's law. So let me make some space here. And let me say that we are in 2.3, apply Hooke's law. Then t is equal to k multiplied by x. We are interested in finding the value of k. Then constructing the triangle of this formula. Then here, because we have multiplied, and t will be at the top, k and x at the bottom. We are interested in determining the value of x. then k is equal to d divided by x. Now we need to find values of t and k. We can choose any value from the table, or since we have the graph, then we can choose any point belonging to this graph. So instead of choosing points that we have already plotted on the graph, and they are telling us using the calibration graph, so we need to choose, it's better to choose a point which is not chosen previously. So let me choose this point. So this is the point A, having the coordinates of 0.1 meters and 1 newtons. So t is equal to 1 divided by the value of x, which is 0.1, so it's given by 10. Since both t and x are expressed in the SI, so the value of k will be in the SI, which is in newtons per meter. Then k is equal to 10 newtons per meters. What does this mean? That this spring has specific stiffness. In order to elongate it or compress it by 1 meters, we need to exert a force worth of 10 newtons. Now, 2.4, the spring being unloaded, we remove this mass. We suspend from its free end a body of unknown mass m1 at equilibrium. The length of the spring is then L1 is given by 17.5 centimeter. Using this previous graph, determine m1. Then we need to use the graph in order to determine the value of m1. So, but notice that here the axes are not either labeled by t, by m, but one of them is t and the other is x. But in order to determine m, think that t is related to m by the following formula, that t is equal to m multiplied by g. So we need to determine t in order to determine m. So if we know x, referring to this curve graphically, we can determine the value of t. Knowing t, then we can deduce m. So let me say that here we have that k is equal to 10 newtons per meter. I don't know if we are going to use again the value of k. Let me see. So let me make some space here again. Now in 2.4, so knowing that the final length is given by 17.5 centimeters, then x, which is equal to L1 minus L0, is given by 17.5 minus 10, which is equal to 7.5. Since both this and this are expressed in centimeters, then this is in centimeters. Then because this is being labeled by meters, we need to convert it to meters. Then 7.5 divided by 100, this is equal to 0.075 meters. Then we know the elongation. Let me say graphically. So usually this is statement, they give it half a mark. For x is equal to 0.075 meters, we have, so 0.075 meters refer to this point on the curve. So now I have noticed that in 2.3 I have chosen a point that is already, I think, given in the table. Okay, it's not important. Now for x is equal to 0.075 meters, we have, so it corresponds to this point on the curve, having a value of the tension T is equal to 0.75 newtons. Now after we have determined the value of T, T and M are related via the following formula. So T is equal to M multiplied by G. We are interested in determining the value of M. And constructing the triangle here, because we have multiply, then T will be at the top, M and G at the bottom, covering our hand with M. So M is given by T divided by G. So this is M1 labeled by the tension T1 for the length L1, then 0.75 divided by 10, this is equal to 0.075. Since both T1 and G are expressed in the SI, so the value of M1 will be in the SI, which is kilograms. So M1 is equal to 0.075 kilograms. So this is it for exercise number 10. Let me move to the next exercise, which is exercise number 11. Consider an elastic spring and a solid S of mass m, given that G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of the Earth. characteristic of the spring. Document 1, they mentioned this document, now we can use it. They didn't mention anything about document 2. We are not allowed to use it, but I think that in the rest of the exercise also they will not mention document 2, but I think we can use them simultaneously. Shows within the elastic limit of the spring the variation of the tension T as function of the elongation delta L of the spring. So what is meant by the elastic limit? So we have discussed previously that the curve of the tension elongation curve stop at some point. This point is the elastic limit, in which it has a tension of 14 newtons and an elongation of 7 centimeters. Now referring to number 1, referring to the graph, complete the table. So let me plot it here. Let me draw the table. So it consists of 1, 2, 3, 4, 4. Then this is the tension T N in newtons, delta L in centimeters. This is K, which is given by T divided by delta L in Newton per centimeter, which is clear here. Now the given values are given by 2, 2, and 6. Now let me complete them in blue. Now, what is the benefit from this curve? If we know the value of T, we can determine delta L. If we know delta L, we can determine T. We always must think of this way whenever we have a given graph. Now, for T is equal to 2 newtons, referring to this graph, we can notice that delta L is 1 centimeter. So this is 1, and the units are included in the first column of each cell of this table. When delta L is given by 2, the value of the tension is given by 4, and whenever the tension is given by 6, the value of delta L is given by 3. So probably most of the cases we can notice always a pattern on the table. Okay, this for whenever the quantities are what are variables, but if the quantity is a constant, no pattern will be found and the value will be constant. Now in this case, K, which is given by T divided by delta L. So for the first values, so this is a ratio. So 2 divided by 1, this is equal to 2 newtons per centimeters. As for the second one, which is given by T divided by delta L, which is equal to 4 divided by 2. And for the third one, which is given by KT divided by delta L, which is given by 6 divided by 3, which is equal to 2 newtons per centimeters. Okay, so as you can notice that because K, we know that K is like a resistance, it's something constant, independent of the value current voltage, so independent of the value tension elongation. So this is 2, 2, and 2. So this is it for number 1. Let me erase. So these are part of the answer, so you must include them on the answer sheet. Now as for number 2, they are telling us that K represents a characteristic physical quantity of the spring. We should not ever forget that the name of K is the stiffness. So they are telling us give the name of this characteristics, so stiffness of the spring. 2.1, give its value in the SI, and notice here the active verb they are using, which is give, not determine or not calculate. Usually whenever they mention give, it means that a small calculation will be involved, or you can directly give it. Then here we know that the value of K is given by 2 newtons per centimeters, but we know that the unit of K is in newtons per meter. Here the unit is combination between newtons and centimeters. Centimeters is not the SI unit of length, it is meter. In order to convert from centimeters to meters, we divide by 100, but this is found in the denominator. and this doesn't hold. So in order to convert from newtons per centimeters to newtons per meter, we need to multiply by 100. Then 2 multiplied by 100, this is equal to 200 newtons per meter. So the value of K is given by 200 newtons per meter. Give the name of the law used or that gives the relation between T, K and delta L, and this is well known as Hooke's law. Now in number 2 they are telling me equilibrium of a solid S. We suspend the solid S from the free end of the spring. S is at rest. Here they must have mentioned document 2, okay, but they didn't do so. Let me make some space above. Now equilibrium of a solid S, we suspend the solid S from the free end of the spring. S is at rest, so at any moment in this exercise we can use the condition of equilibrium. Number 1, give the names of the two forces acting on S. Because we have a mass, then it will be subjected to the weight, which is vertically downward. And because we have a spring, it will be subjected to the tension, what? T. Now in number 2 they are telling me write down the vector relation between these two forces, and whenever they ask us about the vector relation, so they are asking about the condition of equilibrium. So as a title we write at equilibrium. Then on the left hand side of this equation we write the different forces acting on the solid S, and they are given by the weight and the tension. So weight plus tension is equal to 0 vector. Now dragging the tension to the right hand side, we have that weight is equal to minus the tension. Now in number 3, so let me say that K is equal to 200 newtons per meter. Now in number 3 we are asked to deduce the relation between T and M, and by deduce it means that we need to use the previous part, writing it down. Notice that T doesn't include any vector as well as M, so they are scalars. Then we are interested in the magnitude. Now dropping down the vectors and removing the minus sign, we have that the weight is equal to the tension. But we know that the weight is equal to M multiplied by G. In order for M to appear explicitly with T, then T is equal to M multiplied by G. Okay, now part 3. So this is the relation that we are asked for. Now the maximum elongation of the spring within its elastic limit is given by 7 centimeters. So the maximum elongation is given by 7 centimeters. If we suspend a mass of 1.7 kilograms, the spring loses its elasticity. Justify referring to the curve. So here, since they mentioned the spring will loses its elasticity, so they are talking about the functioning of the spring itself. Okay, whenever they mention losing its elasticity, which means that the applied tension or applied force is greater than the maximum force within the elastic limit of the spring that it can handle. In order, if you recall that this can be understood by referring to the electricity. So whenever we talk about the functioning of the lamp, we need to compare the applied to the rated or the applied to the maximum. So here it's the same. We need to compare the applied, which is the mass, which is given 1.77 kilograms, to this one. But this cannot be compared with this unless they have the same unit. So this must be represented in a unit, and this must be represented in a unit in which both are of the same quantity. Then we can compare them to each other. Now 7 centimeters, which is the elongation referring to the curve, we can determine the tension. Now 1.7 kilograms, we know that we can compare that we can calculate also the tension because we have the relation between Tm and G. So from this we can calculate the maximum tension, and this we can calculate the applied tension. Comparing the applied tension to the maximum tension, we can deduce that the spring will lose its elasticity. Then because T is equal to M multiplied by G, which is equal to 1.7 multiplied by 10. This is equal to 17 newtons. So this is the applied tension. Now graphically, for x is equal to 7 centimeters, we have, so here they are denoting the elongation to be delta L not x. Let me use the same notation. So delta L 7 centimeter, which correspond to this point on the curve, having the value of 14 newtons, knowing that the curve allows you to determine the value of this, as whenever you know one, you can determine the other, and vice versa. So this is the maximum tension. And now we can safely say, since the applied tension is greater than the maximum tension, between brackets 17 newtons is greater than 14 newtons, then the spring loses its elasticity. And now let's move to the next exercise, which is exercise number 12. So in this exercise, they are telling us an iron ball of center of gravity G and of mass M is equal to 500 grams. Then the mass 500 grams, in order to convert it to the SI, we divide by 1000. Is connected to the free end of a spring balance dynamometer of stiffness, force constant K is equal to 100 newtons per meter, and take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of Earth. In order to elongate or compress the spring by 1 meters, we need to exert a force of 100 newtons, and knowing that each kilogram on Earth is being exerted by force of worth 10 newtons. Now number one, okay, before we refer to the exercises, let's look over the exercise overall. We have M and we have G. We can determine the weight. From the weight, because it is at equilibrium for sure, we can deduce the tension. Knowing the tension and knowing K, the elongation can be deduced using Hooke's law. Number one, the ball is at equilibrium under the action of two forces, so at any moment in this exercise we can use the condition of equilibrium. One of these two forces, it's the weight W of the ball, name the other force. So because we have a spring, then it will be submitted to the tension T. Give the line of action and the direction of the weight and calculate its value. So the line of action, here we are discussing the weight. We know that always the weight acts vertically, downward, and the direction is what? Downward. As for the value which means the magnitude, and notice that these are part of the Pildim, and I have listed them. I have respected the order, which is the Pildim, so LDM. Now the magnitude can be determined from M multiplied by G. Then weight is equal to M multiplied by G, which is 0.5 multiplied by 10, which is equal to 5 newtons. Now in 1.3, they are telling us to write down the relation between the force vectors at equilibrium. So because it is a relation between vectors, we will write at equilibrium that the weight plus the tension vector is equal to 0 vector. Now dragging the tension to the right hand side, so weight is equal to the minus the tension. So we don't mention anything about the magnitude because they are asking us for the vector relation. And what's the type of this equation? This is a vectorial equation because it has an equal and vectors. Now in 1.4, they are telling us to find the elongation of the spring. We don't have the initial length nor the final length, so the only way to determine the elongation is via Hooke's law. In order to calculate x via Hooke's law, we need to know K and T. T can be determined from W from this equation. So weight is equal to the minus the tension. So let me say in magnitude, that the weight is equal to the tension, but we know that the value of the weight is equal to 5 newtons, then the value of the tension here 5 newtons. Now apply Hooke's law. So we have that T is equal to Kx1, and we are interested in determining the value of x1. Now constructing the triangle of this formula, here because we have multiplied and T will be at the top, K and x1 at the bottom. Putting our hand over x1, then x1 is given by T divided by K. Then dividing T divided by the value of K, which is 100. So the value of x1 is given by 0.05 after plugging this on the calculator. Since both T and K are expressed in the SI, so the value of x1 will be in the SI, which is meters. So x1 is equal to 0.05 meters. Now in number 2, they are telling me a magnet is now placed on the vertical line passing through G. A magnet is now placed on the vertical line passing through G. So this is the vertical line passing through G. So whenever we say the magnet is placed, so the magnet is either can be placed here inside the spring or here. So it either will pull the magnet upward, the ball upward or downward. It pulls the ball with a force F. So the force F will be upward or like this, downward. Now the elongation of the spring balance becomes x2 is equal to 8 centimeters, which is equal to 8 divided by 100, which is equal to 0.08 meters. Now in 2.1, find in this case the value of T2 of the tension and the spring balance. Now T2 can be calculated using Hooke's law because we know the value of x2 and we know the value of the stiffness. So apply Hooke's law. Now T is equal to K multiplied by X. We are interested in determining the value of T. No need to construct a formula. This is labeled by 2, this is by 2. Then 100 multiplied by x2, which is 0.08, which is equal to 80 newtons. So T2 is equal to 80 newtons. Now in 2.2, they are telling me by comparing T2 and W, so let's compare the values of T2 and W. The value of T2 is given by 80 newtons, whereas the value of W is equal to W was given by 5 newtons, and by compare we need to say whether one is greater, less than or equal. So in this case it's clear that T2 is greater than 8. T2 greater than W. Using this result, we need to show that the magnet is under the ball. So here let me explain the following. We need to deduce whether the magnet is under or above the ball. Now notice the following. The tension is acting upward and the value of the tension is how much? T is 8 and W is 5. So T2 is 80 newtons and the weight which is acting like this is 5 newtons. Now taking a look at the values, we can notice that T2 is stronger than W, and this has been deduced from this, and they are telling us that the ball is still at equilibrium, although it's not mentioned here, but they meant for sure that the ball is at equilibrium. Now, so in this case, for the ball to be at equilibrium, there must be something helping the weight to balance the effect of the tension, and this difference must be 3 newtons, and these 3 newtons must be downward, so we need to add the 3 newtons more on 5 in order to balance the 8. So for sure the force F that we are talking about, which is due to the magnet, must be downward like this. So this is the magnet and it must be downward like this in order to help the weight. So for this reason the magnet must be under the ball. Since the weight is acting vertically downward, and the tension is acting vertically upward, and knowing that T2 is greater than W, then the magnet must be placed under the ball, in this case F, which is the magnetic force, acts vertically downward, to balance the actions of T2 and W. So this is it for this exercise, and let's go to the final exercise for this part, which is exercise number 13. A spring perfectly elastic, so whenever we say perfectly elastic, it means that we can apply Hooke's law, has a stiffness of K is equal to 10 newtons per meter. So we know the value of K, and its upper end O to a support, a solid of mass m, is equal to 100 grams. Then we know that in order to convert from grams to kilograms, we need to divide by 1000. Is suspended to the lower end A of R, as shown in document 1. S is at equilibrium. Take G is equal to 10 newtons per kilogram, which means that we are performing this experiment on the surface of the Earth. Now, taking a look at the values, knowing M and G, we can determine weight. Knowing the weight, we can deduce T from equilibrium condition. Knowing K using Hooke's law, we can determine the elongation. Number 1, S is submitted to two forces, its weight W and the tension T of the spring. 1.1, reproduce the figure of document 1 and represent these forces without a scale. So it's here, no need to represent all the figure, it's just sufficient to represent the solid S like this. And it's important to label the points. This is the point A. For example, here you can draw this hook and place the point A, but it's not important. We can just draw it like this, and this is the point G. Now we know that the tension will be acting so the tension will be acting at the point A vertically upward like this, and the weight will be acting vertically downward like this, okay? But here the thing is that what makes this answer correct or wrong is the following. Notice that I have represented the weight using 3 divisions. So 1, 2, and 3, and the tension with 1, 2, and 3, which means that the length of the tension is equal to the length of the weight, which means that both magnitudes are equal, which reflects the fact that the solid S is at equilibrium. The number of divisions is not important. We could have represented T with 2 divisions or the weight with 2 divisions, but what is important that the number of divisions which reflects the magnitude must be equal. Otherwise, if we represent the tension using 2 divisions and the weight with 3, this is considered to be wrong. Now in 1.2, we need to tell for each of the T forces whether it's a contact force or force acting at a distance. We know that the only 3 forces act at the distance are given by the way, the electric, the magnetic, so this is acting at a distance. And all other forces are classified as contact forces, and in particular the tension T. Now in 1.3, we need to calculate the magnitude W of W, so the weight, which is the magnitude M multiplied by G, then 0.1 multiplied by 10, this is equal to 1. Everything is expressed in the SI, so the value of the weight will be in the SI, which is in newtons, so W is equal to 1 in newtons. Now in 1.4, we need to show that the magnitude T of T is 1 in newtons. The magnitude, for example, can be calculated using Hooke's law. Unfortunately, we don't know the value of the elongation, so it cannot be determined using Hooke's law. Then we need to refer to the condition of equilibrium. Then let me say at equilibrium. we have that the weight plus the tension is equal to 0 vector. So the weight is equal to the minus the tension. Since we are interested in magnitude, so let me say in magnitude, the weight is equal to the tension, but the value of the weight is equal to 1 newtons. Then in this case, the value of the tension is also equal to 1 newtons. So T is equal to 1 newtons. Now after we have, okay, so this is it. We stop here. Let me make some space. Now the initial length is given by L0 is equal to 20 centimeters, equivalent to C is equal to 0.2 meters, and the SI. Determine in centimeters the elongation delta L. Delta L can be always determined using two methods, either delta L is equal to final length minus initial length, or using Hooke's law, which is delta L is equal to T over K. We don't know the initial length, then we need to refer to this formula because we know T and K, and this is done by using Hooke's law. Apply Hooke's law, then T is equal to K delta L. We are interested in determining the value of delta L. Then constructing the triangle of this formula here, because we have multiplied, then T will be at the top, K and delta L at the bottom. We are interested in determining the value of delta L. Then delta L, which is T over K, the value of T is given by 1 and the value of K is given by 10. So this is equal to 0.1 meters. And they are asking me to calculate delta L in centimeters. Then in order to convert from meters to centimeters, we multiply by 100. So from centimeters to meters, we divide by 100. But from meters to centimeters, we multiply by 100. Then 0.1 multiplied by 100, this is equal to 10 centimeters. So delta L that we have calculated is equal to 10 centimeters. Let me make some space. Now in 2.2, we need to deduce the final length, and in order, deduce means that we need to use the previous part. So delta L and the final length are related via the following formula. We are interested in L. What's the type of this equation? This is a linear equation in one unknown. We know the value of delta L to be 10 in centimeters, and the initial length is given to be 20. So what's the type? Okay, so how do we solve it? We put L on one side and all the others on the other side. Then dragging 20 to the right hand, to the left hand side, it will be plus. Here it is minus. Then L it's equal to 10 plus 20, which is 30. So this is expressed in centimeters and this is in centimeters. So this is in centimeters, but we know that the SI unit of length is meters. So L, which is equal to 30 centimeters, dividing by 100. So this is 0.3 meters. Now in number 3, R can be elongated to a maximum value of delta L max, which is 15 centimeters, which is 0.15 meters. Without losing its elasticity, determine the maximum mass and max that could be hung at A. So knowing delta L max, we need to determine max. So how come? Delta L max, knowing delta L max, we can determine T max. Knowing T max, we need to determine W max. W max, knowing W max, we can deduce M max. Okay, so we will move in this algorithm. So let me say apply Hooke's law. Then T is equal to K delta L. No need to construct a triangle. This is max and this is max. The value of K is 10 and the value of delta L max is 0.15. So this is equal to 1.5 newtons. And we know that the weight is equal to the minus the tension. So in magnitude, weight is equal to the tension, but we know the value of T max is equal to 1.5 newtons. Then in this case, W max is equal to 1.5 newtons. So now knowing W max, we can deduce M max. So W is equal to M multiplied by G. We are interested in M. Then M max is given by W over G, which is 1.5 over 10, which is 0.15. Both this and this are expressed in SI, so the value of M max will be in SI, which is kilograms. So M max is equal to 0.15 kilograms. So that's it for me in this video, guys. In part 5, we'll complete the explanation of this chapter and introduce the principle of interaction.